Now, did you get the record message, Anirban? Now I'm starting the record. I don't know whether it
Oh,
is
yes,
recording or
yeah,
not. Yeah,
yeah,
you got? Yeah, I see, I
yeah.
see. Oh, okay. Let me start the today's first seminar. The first speaker is Professor Anirban Das from Saha Institute of Nuclear Physics. In this talk, he will talk about quantum devices to detect light dark matter. Please start when you are ready.
All right. Good morning. I guess it's good afternoon, everyone. And I'm very happy to hear, and thanks to Jehu for the invitation to give a seminar at KIAS. So this talk will be about a couple of papers that I wrote with my colleagues at SLAC. It's about using small superconductor-based quantum devices to detect light dark matter, actually using a new way of detection, new way of doing direct detection experiments for dark matter particles. So to begin with, we all have the evidences of dark matter at various different length scales in our universe. We start from the very small galactic length scale we have seen in our Milky Way itself, and also in many other galaxies, Milky Way-like galaxies, which shows us that there is a clear discrepancy between the observed rotation velocities of the stars around the center of the Milky Way and the calculated one, which assumes just like normal ordinary Keplerian gravity. And if you just sum up all the masses that's within the orbit of a particular star, and then you can calculate the radial velocity of the star, you get this red this not to scale is just a cartoon diagram for the rotation velocities, but you get something like this. The rotation velocities, it first increases from the center, but then after some time it decreases and drops down as there is no more stars after a certain distance. But from observation, we see a very different curve. We see a more or less constant. The curve kind of saturates to a constant value at large distance. So this means basically there is a missing mass. Something is there, more gravitating mass is there in our galaxy. And to a larger scale in the galaxy clusters, we have also seen the gravitational lensing, where you see the distant galaxies, the lights from the distant galaxies coming through the through another galaxies, or which that like another massive galaxy which is sitting in the intervening medium in between us and the distant galaxy. And we see these lensed images of those galaxies. For example, this particular image is from the JWST survey. It's a very recent one, and you can see some of these stick-like narrow images are gravitationally lensed. So which clearly tells us that there is more mass in this intervening medium in the galaxy clusters, which is at the center of the image. And finally, at the larger scale, in the cosmological length scale or the cosmic horizon scale, we have the cosmic microwave background observations. So for several decades now, many different experiments, COBE, WMAP, and finally Planck, has measured the power spectrum and also the photon energy distribution, the Planck distribution, very accurately, very precisely. And if you want to explain the statistics of this measurement, you need to assume the existence of a massive a component in the universe which is massive and cold, which we call the cold dark matter. So all these evidences point to this existence of roughly 27% of the universe to be in the form of dark matter. Now, knowing that evidence is one thing, but actually identifying the nature of the dark matter is a totally different game. So the first question that we have is what is the mass of this and what's the nature, like whether it's particle or like some kind of wave or some macroscopic objects like primordial black holes. And there are several, not several, I mean, I guess thousands of different models for dark matter at this point in the literature. And the total mass range, which is valid today, spans over 90 orders of magnitude. So it's starting all the way from 10 to minus 22 electron volt to tens or hundreds of solar mass right now. And the dark matter candidates are also very different in different mass regions. And by the way, if you have any questions, feel free to stop me anytime. I'd be happy to take questions. Now, even though all of this mass range is equally valid right now, but we have not explored the whole range equally. So historically, there have been, for theoretical reasons or some maybe academic social reasons also, in some particular mass range, we have done a lot of experiments, and we have explored a lot of the large part of the parameter space. So one of these example is this WIMP regime, or typically within the 10 GeV to 10 or 100 GeV mass range. In this range, the dark matter has to be particle. And there are several experiments going on around the world. Probably you know the names of some of them: Xenon, Lux Zeppelin, Panda X, and Kusain, which is in Korea itself. And the main idea behind all these experiments, the working principle is basically they have a large detector with some detector material, which varies from experiment to experiment. But the idea is that the dark matter, which is coming from the halo around the Milky Way, will come and scatter with one of the nuclei in the detector, and this nucleus will then recoil. We cannot see the dark matter because it does not interact with standard particles very strongly, but we can see the recoil of the nucleus, and that will give us that will be the signature of any the existence of dark matter particle. Now, from this observed rate of this recoil of nucleus, you can get some idea about what is the coupling constant or the scattering cross section between dark matter and nucleon. So this is a very famous parameter space in which all of these experiments show their constraints. So the x-axis is the dark matter mass or width mass, and the y-axis is dark matter nucleon scattering cross section. And this one is the latest one from Lux Zeppelin experiment, which came out a couple of years back. And I believe this is the strongest one right now. And it goes all the way to 10 to the minus 47. And there are several other experiments. And as these experiments keep going on, they also improve their sensitivities. But that's not the whole part of this mass range, right? As I said, there are other parts, and this another interesting region of this parameter space is this light dark matter, sub-GeV dark matter, which is not largely explored yet as compared to this WIMP regime. But it's not because there is no possible dark matter model in this mass range or anything like that. It's just because it's been hard to do any experiment in this mass range, and I'll get to why it's difficult. So here I'm just showing two plots of latest NOMAS report. The left one is between dark matter electron scattering cross sections. So because we do not know whether dark matter interacts with any standard model particle at all, we have to put forward some hypothesis whether dark matter interacts with electron or nucleon or maybe both. So when we do experiments, we do different types of investigations, and we get constraints in the dark matter electron scattering cross section or dark matter nucleon scattering cross section. So the left one is dark matter electron, and the right one is dark matter nucleon. And if you look at the mass ranges, you can see that the typically like for electron, because electron is light, below like 100 MeV or tens of MeV, the constraints this parameter space opens up hugely. So this solid black line is a region which is currently excluded, and all of this part is not excluded right now. Similarly for the dark matter nucleon. So if you go below GeV, there is almost nothing here. But nowadays, for last maybe a few years or maybe several years, there has been an explosion of ideas to do experiments in this light dark matter sub-GeV dark matter regime. And this is what is shown here in this plot. So this green region is the near term. Near term means maybe we can explore this part of the parameter space within 5 or 10 years. And far term is that's gonna take even longer. And this orange band is typically some theoretical models which predict the dark matter sand model cross section in this part. So so even though we do not have any constraints in this part, but hopefully within the next decade or so, we'll have something. And I said that it's difficult to do experiments below GeV mass, GeV dark matter mass. And the reason behind that is because we know that dark matter is non-relativistic, it's cold. So the typical kinetic energy is just non-relativistic one, half mv square. So when we look at lighter dark matter, the kinetic energy also goes down, proportional to its mass. So when you go below GeV, the energy also goes down, and this energy is not sufficient to scatter with a nucleus. So the nuclear recoil will be very, very tiny, and our experiments are not sensitive enough to pick up that signal. So we have to do different types of experiments. So we have to change our technique. So there are other excitations in the condensed matter area which we can use to detect a sub-GeV dark matter. So here are just two of these examples. There are many others, so I'm just showing you two very famous ones. So one is phonon. Phonon is basically a quantum of crystal oscillation. So most of these materials, detector materials that we use today, they are crystals. And any crystal, it can have the crystal lattice will have thermal motion, and they will have phonons. So when we go below, so these equations, they show the typical energy of dark matter. So as I said, this just scales with dark matter mass. So MEV dark matter will have sub EV energy, and similarly for momentum. And if you and this is the energy momentum relation of generally speaking, and this phonons, if you calculate now you can go and calculate the typical phonon energy momentum relation, or what's called the dispersion relation of phonons, and you'll find some region of this energy momentum parameter space where phonons you can excite phonons. So this is just one example. It's typically within 10 to 100 millielectron volt. And another interesting channel would be electron hole pair excitation. So in this case, you have dark matter has to interact with electrons, and if it interacts with electrons which is sitting in the valence band, it can transfer some energy, and then that electron can jump to the conduction band, and that will be the signature of dark matter recoil. And typically semiconductors, for example, they have this energy band gap, the gap between the valence band and the conduction band, in the range of 100 millielectron volt to EV scale. So these two are two of the most famous collective excitations in low energy systems that people are right now using to do experiments to look for sub-GeV dark matter. Now, those are all like difficulties that comes with light dark matter, but there are also some upside for light dark matter, which is the number density. Now, as I said, we do not know the mass of dark matter, so that tells us And all these experiments, they are sensitive to the number density of dark matter, not the total energy density. We know the total energy density, but to get the number density, we just have to divide by the mass of dark matter because it's non-relativistic. So when you have, so we know rho, we know the total energy density at the position of the sun, which is roughly 0.4 GeV per centimeter cube. And we divided that by the dark matter mass. So if you have light dark matter, that means your number density is large. So that's a good thing about doing um, uh, low mass experiments is that the number density is high. So you do not need a large detector mass like xenon or xenon or LZ. You can do a relatively small scale experiments. Like for example, some of these experiments have 10 gram or gram scale uh, active mass of detector, and still you can have the the leading constant in the dark matter standard model scattered cross section. So that's a good thing about this part of the biological space. Now let's get to our proposal of using power deposition. Now to differentiate these from the conventional techniques, as I said, all of these experiments. So here are just a few other experiments which are currently going on right now in the sub-GeV range. So Sensei, Grace, Super CDMS. But similar to these other xenon-like experiments, they are also looking for single recoil of dark matter. So the idea is that dark matter comes and scatters with either nucleon or electron, and you look for the recoil signature from that scattering. And that's the same for all experiments. Now, we want to do different, because we want to use the current technical ability for some of these quantum devices that we have. And I'll show that we can do that. And that actually gives us very competitive limits already without any dedicated dark matter experiments. So the idea behind using the power deposition is the following. So in this normal other conventional dark matter detection experiments, we calculate the total scattering rate. So this is the spectrum rate. I mean the rate of dark matter scattering per unit energy interval, and you integrate that over the energy with the energy, and you get the total scattering rate. But in this case, we do the same integral, but just adding one factor of energy. So that gives us a total power. So we are not looking for this individual recoil signal. We are looking at the collective power deposition by multiple scatterings of dark matter particles inside the detector. Now, of course, we are going to look for halo dark matter because that's a primary motivation for any dark matter experiments. But there is also another.
Sorry. Can I ask one question? In the previous page, I don't understand what is the difference between these two quantities. Definitely, you said in the left quantity, just we multiplied by one energy more, but why this quantity uh just implies such kind of noise? Yeah, would you please explain
Uh,
more?
Sure. So you said why it introduces noise?
Yes, yes. In this
Oh, so
quantity, yeah, yeah,
right. So
yeah.
this is probably not the best way. This is probably a like a misnomer. We shouldn't actually call this a noise. What I
Mm,
meant to say is that it's so we are not looking for single recoil signal from
mm,
dark matter scattering.
mm, mm,
Our signal would be like an overall power deposition, like a
mm,
constant with time constant uh, power background
mm,
over the expected power uh, uh, from other sources. Of
mm,
course, there are other backgrounds, so we have to isolate that other background from the dark matter injected power, and that
mm,
would be the signature in this type of experiments. So
mm,
in
mm,
that sense, it is kind of like qualitatively it's like a noise. So that's why actually when you started working on this, we are calling this noise. But noise is probably not the best term here. But mathematically they are kind of similar. So it's like additional constant power in the system
Mm.
over the background sources.
Mm. Ah, so such kind of effect is related to why we need to multiply one more energy in the PDM form, right?
Yes, right.
Ah,
Yeah.
yeah, yeah, yeah,
So
yeah.
yeah, yeah. So the units of this quantity T gamma over T omega
Mm,
is just
mm,
uh, um, hertz per EV or whatever energy scale.
mm,
So gamma is the rate, so hertz or whatever second. And
mm,
if you do this total integral, you just get this watt. You get either watt or if it's just per unit volume, then you get watt per unit volume. So that would be the main that's actually the units for this PDM. When I say power, I mean watt per unit volume.
네,
mm.
여보세요?
I see.
Is there another question?
아, 관심 없습니다.
Sorry, I think, yeah,
Okay,
Professor Ungjin didn't notice that. Yeah, anyway, thank you. Yeah, yeah. I partially understand.
all right. Yeah.
Yeah, thank you. Yeah, please go ahead. Yeah.
Right. So as I was saying, there is another population of dark matter that can be probed in these devices, and that's because these devices typically have very low energy threshold, and that's called the capture dark matter or thermalized dark matter. And this happens in some particular dark matter models where the interaction coupling between dark matter and standard model is relatively strong. So in the upper parts of this parameter space that I showed in the where the y-axis is the dark matter nucleus scattering cross section. So when the cross section is large, what will happen is over the like billions of for example, our Earth is billions of years old, and over the age of this object, so this dark matter and they'll scatter with the crust of the or the whole of the Earth. And some of these particles will lose energy and get captured gravitationally in the neighborhood of the object. It can happen in Earth, and actually can happen in any astrophysical objects. And over time, there will be a buildup of population of dark matter, which is totally thermalized with the local temperature of the system. In case of Earth, so that temperature is roughly 300 Kelvin. And then you can compare what is the parameters between this thermalized dark matter population and the halo dark matter. Even if you take the same mass, let's say 1 GeV, the typical energy of this population would be much lower. So in the milli-electron volt range. And because, as I said, the temperature is very low, 300 Kelvin. But again, here the advantage is that because this process is happening over many years, there will be large population buildup. The typical number density that we can expect for this thermalized dark matter could be upwards of 10 to the 10 per centimeter cube. And in some parts of the parameter space, this number can go all the way to 10 to the 14 or 10 to the 15 per centimeter cube. So which is a large number. And compared to halo dark matter, for example, 1 GeV dark matter, for the energy density of 0.4 GeV per centimeter cube, you can expect only 1 per centimeter cube. Compare that with 10 to the 10, which is very large. So here again, you need to look for this population of dark matter. You need very low energy threshold devices because the typical energy of this particle is very small. But then because the number density is very large, you do not need very large device. You do not need large detector mass to do experiments. You can have a very tiny millimeter scale or micrometer scale device, and you can do some exciting experiment with that. Right. Now let's get to the details. As I said, phonon excitation is one of the ways to detect light dark matter. And here's just a bit more idea here to how that works. And we are going to use superconductor traditional conventional superconductor devices. So dark matter scatters in this superconductor and it excites phonons because it does not have enough energy for a single nuclear device. So it will either excite a single phonon or multiple phonons of various different energies. And in a superconductor, these phonons and the Cooper pair. So Cooper pair is the ground state of these superconductors where two electron pair, like a pair of electrons, they are coupled together or bound together by a phonon interaction. That's a long range interaction. And now we can see that when you deposit a bunch of extra phonons in the systems, these phonons will then mix with these phonons within the Cooper pair, and that they can break some of these Cooper pairs. And when a Cooper pair is broken, it releases this charged particles, and these are called quasi-particles in the community of condensed matter. And these quasi-particles can be detected by some sensors. So one of those examples is transition age sensors, and nowadays we have very good sensitivity or very highly precise sensors which can detect even single quasi-particle excitation in a superconductor. So you can use that. So that's the idea. So dark matter comes and scatters, excites phonons. These phonons will then break some of these Cooper pairs, they release quasi-particles, and these quasi-particles will be detected.
What is A?
A is the lattice spacing of the system. So typically we'll use either aluminum or silicon, and it's of the order of angstrom. And so I'm just writing here this line is because for low mass dark matter, the typical momentum, it matches well with the typical lattice spacing. So the momentum transfer from the dark matter to the lattice or phonon excitation is very favorable. So that's why the phonon is one of the interesting way to look for dark matter scattering.
Okay, so here also dark matter should communicate with the electron with like a photon, like how this
so
dark
in
matter
this,
collide, interact with the
in this case, we are not considering dark matter electron scattering. We are considering dark matter nucleon scattering because we want to use the phonons. I mean, but there is nothing wrong with dark matter electron. It's also possible in some dark matter models. And if you have dark matter electron scattering, in that case, you can, so in that case, dark matter will directly interact with this, with the constituents of this Cooper pair. And in that case also, you can get some quasi-particle excitations. But in our work, we consider dark matter nucleon scattering. So we have to first excite phonons because if dark matter primarily it interacts with the lattice sites or the nuclei, then the phonon excitation is the primary channel, primary collective excitation. So once phonons are excited, these athermal phonons, then they can interact with the Cooper pair and break them and release quasi-particles.
I have a following question. Yeah, then
Sure.
you means in your consideration, you didn't consider the scattering between dark matter and electron in this your work.
Not directly. Yeah, there's no direct coupling between dark matter and electron.
If we consider such a scattering with the electron, then we need to consider more scenario or another how should I say another momentum transfer or another signal, something like that.
Yes, so you can on top of this.
Yeah, please tell me.
Yeah, so on top of this, you can actually consider dark matter electron scattering, and in that case, the calculation will be different, the mechanism will be different. So in that case, you have to look at the BCS, basically the ground state of this conventional superconductor, and you have to figure out how that scattering will disturb the ground state of the system, and what would be the quasi-particle excitation rate. And you can do that. That's totally fine. And that would be an additional signal on top of this.
Even though we consider the electron scattering, still phonon interaction can be generated. This is kind of very naive question.
I see. So you saying that if dark matter only scatters with electron, whether you can excite photons?
Is it possible?
I believe that would be a bit difficult, because in a lattice, I mean, if you forget about the superconducting nature of the crystal, if you in just a normal lattice, the coupling between electron and phonon is not that strong, because you see the phonons live in the lattice space, right? It's basically the vibration or the quantum of the vibration of the lattice. So phonon means just the nucleus.
Yeah, nuclear fluctuation. Yeah.
Right.
Yeah.
And the electrons are basically clouds which are localized around these lattice sites. And the coupling between this electron cloud and the lattice is not that strong. So if dark matter if dark matter interacts with this electron cloud, only a very small amount of energy might be transferred to the lattice sites.
I see.
So I don't think that would be an observable signal. So in that case, you have to look at something else.
I see. Thank you. Yeah, I understand. Yeah.
So in this case, the deposited energy in the form of phonons can be transferred to the quasi-particles much more efficiently, because it's a superconductor. So because in a superconductor, there is a state called Cooper pair, where there is a mixing between electrons and phonons. Because of this strong mixing, you can then transfer a large part of energy. That's actually its phenomenology roughly has been 60%. So when there is an energy deposit, or about 60% of that gets transferred to quasi-particle excitation. So this number is relatively large because of the existence of this ground state, the BCS ground state of superconductor. In a normal lattice, this will not be possible.
I see. Yeah. Thanks for explanation. Yeah.
Okay. Right. I think so here I'm just showing just one example of phonons. There are typically two different types of phonons: acoustic phonons and optical phonons. But it's not really needed to understand the mechanism here, so I'm just going to skip that. And right. So now you have to calculate. So that's a picture. Now we have to calculate what's the phonon excitation rate. So that's the first step in calculating the dark matter scattering rate. And this is the formula to do that. It's quite simple to understand. It's just proportional to the dark matter number density, proportional to the scattering cross-section, sigma n. We integrate over the dark matter velocity distribution. So in the in the Milky Way halo, it's supposed to have a Boltzmann distribution with roughly a mean velocity of 220 or 130 kilometers per second. And finally, there's a momentum integral. And there are two components inside this integral. One is this structure factor. And this quantity here, let me first explain this. So this is a form factor, which just depends on what is the mediator of the interaction. So it's a mediator between the nucleus and the dark matter. And if it's just a point-like interaction, so heavy mediator, then this form factor is just 1. If it's light mediator, this form factor goes as 1 over q squared. And the structure factor here, this S thing, it contains all the information about the system in your experiment, whether it's aluminum, silicon. So everything is contained within this. So it just basically means what is the response of the system when you deposit an energy of omega q and a momentum transfer of q. And this can be calculated from first principle either from first principle, if the system is simple enough, or you can do an experiment and measure this quantity directly. And in our case, because we are using crystals like aluminum and silicon, which are also widely used in dark matter experiment community, and we can calculate, they're actually taken from this paper, where inspired from neutron scattering, you can calculate this structure factor in various different regimes of momentum transfer. So this, when Q is smaller than QBZ. So QBZ means 1/A, where A is the lattice spacing. So BA, so momentum. When Q is smaller than that, or Q is bigger than that, you can have different analytic approximations for this structure factor. And this is what that structure factor looks like in the energy momentum space. This the left one is for aluminum, the right one is for silicon. Aluminum has only this acoustic branch at low momentum. Silicon also has this additional optical branch because their crystal structures are different. And at large momentum, there are multiple phonon excitation possible. So that's why this bright yellow region in both of these cases. And on top of this, I'm showing these dashed white lines. These are the dark matter phase spaces. So for this thermalized or captured dark matter, which I explained a few slides back, for two different mass scales of dark matter. So you can see that, so it basically means that dark matter lives around these lines, in this dashed white lines. So you can see that there's a relatively large overlap between this bright region of the structure factor and the dark matter phase space. So which means that we can have a good sensitivity in these crystals. Now, so that's a power deposition technique. Now let's get back to the superconducting devices. So in any superconductor, at a certain temperature, there is an equilibrium set up between the Cooper pairs and the quasi-particles, which I explained before. So here's a cartoon of this equilibrium. So these are the Cooper pairs and these are the excited quasi-particles. When you break a Cooper pair, you release two quasi-particles. And in equilibrium, you can write down, actually not in equilibrium, in general, you can write down this Boltzmann equation for the change in the number density of these quasi-particles. So these terms are for different source terms. So this one is for when two quasi-particles recombine, they form a Cooper pair. This for trapping, where the quasi-particles get trapped into some other source in the system. And this one is for if there is any additional energy source in your system. So in our case, this could be the power injected by dark. So, and we divide this by these deltas. Delta is the energy required to break a Cooper pair. So that's the superconducting energy gap. And when there is an equilibrium in a steady state, you can drop the left-hand side, and you can get a relation between this dark matter power injection and the quasi-particle density, and that gives us this equation of this relation between number density and power injection. So you can see that you can get to very low power density or power deposition rate for these devices, 10 to the minus 21. And now let's get back to, so that was all the theory, how we are going to calculate the power deposition or scattering rate for dark matter. And now if we have to constrain the dark matter nucleon parameter space, we have to use some real world data, some actual data. And for that, because there is no existing experiment that has taken data for the purpose of dark matter, we have to use the data from some other areas or some other experiments. So in our paper, we use 3 different experiments. The first one is from this paper. In this work, they were just trying to do, so this is not a dark matter paper at all. It's a condensed matter paper where they were trying to devise or fabricate a qubit called a special type of qubit called transmon qubit, which is superconductor based. And these quasi-particles are background in their case. So they do not want, they want an environment without any quasi-particle poisoning at all. So they are trying to reduce this quasi-particle background. And they found a very low number, which is 0.04 per micrometer cube. And if you then, as I said, as I showed in the previous slide, you can convert this number density to a power injection, and that gives us a 10 to minus 24 watt per micrometer cube. And these are very small numbers.
What would the background in this case? Or the quasi-particle background?
So, sure. So in this particular experiment, they do not do their experiments in any underground lab. So typically it would be in some lab, some university lab, without any substantial amount of shielding. So you'd expect some cosmic ray background, also possibly some environmental radioactive backgrounds.
But this is qubits, so they should be shielding, right?
There is some amount of shielding. What I'm saying is that their shielding is nothing compared to the typical shielding you see in any dark matter experiment. So the level of background would be much higher than a dark matter experiment. So that's a good point actually. So this qubit community, they did not realize early that this cosmic rays, for example, is going to be a huge background for them. So they only realized this only maybe 4 or 5 years back, that cosmic rays are actually one of the main thing that's limiting their advancement in qubit research. So their motivation is different, right? They want to build a qubit with as many, they want to build a qubit chip with as many qubits as possible. And they want to maintain quantum coherence among all these chips for as long as possible. So their coherence is needed for in a large, like relatively speaking, a large part of space and also a large part of time. And this cosmic rays still is one of the limiting factor for that. So because once in a while, one of these muons in the upper atmosphere will come and deposit energy, and that will break the coherence. So in all of these qubit experiments, they will see in a regular interval period, there will be a loss of coherence in whole of the qubit chip. And but now they have realized, so nowadays they are trying to do their experiments with proper shielding, and also not only just cosmic rays, but also some stray photons from the environment, also radioactive backgrounds. Yes, so they also have backgrounds, and those are pretty similar to our backgrounds also in dark matter. But still, we saw that in the existing literature, this is like one of the lowest power density that we have measured, and this is actually going to be very crucial for our results also. For the second experiment, we looked at another paper where they are trying to develop a single photon sensor for space astronomy. So this in their case, they also have a superconducting aluminum, and they want to build a single photons, and this is needed for telescopes like JWST, where they can detect very faint sources where the number of photons coming in is very, very small. So in this case, they were calibrating their sensor, and this is a plot from their paper. The x-axis is expected photon rate, and the y-axis is what's the actual number of photons detected. And at low photon emission rate, you do not expect to see anything, but still they see something, some residual dark current. And that also gives us another number, 10 to minus 20 watt per micrometer cube. And this is not, you can see this is not as sensitive as this one, but still it's up there. Now the third one is actually a dark matter experiment. It's called Super CDMS. Their system looks something like this. This is a cartoon, a schematic diagram. Their substrate or the main detector material is a silicon, which is covered with superconducting aluminum, which is this gray part, rectangular part. And this is again connected with this very high sensitive TES detectors, transition edge sensors. So these are the devices which can detect these quasi-particles. So in their case, their idea is actually very similar. So dark matter scattering will happen in this substrate, in the silicon, that will dump some phonons. These phonons will then break Cooper pairs in this aluminum and release quasi-particles, and these quasi-particles will be detected in the TES. But for our in our case, we are not looking for recoil. We looked at the calibration data for this super CDMS detector, and in their paper they observe an excess energy of roughly, I think, is a few picowatt, and we took that number and calculated what is the quasi-particle density, and then that gives you a power density of roughly 10 to the minus 21 watt per micrometer cube. This is again not as sensitive as the qubit one, but it's better than the previous one. This is the single photon detector. So we use these three numbers as to put limit on the dark matter nuclear scattering cross section. And this is what that looks like. The x-axis is dark matter mass, the y-axis is dark matter nuclear scattering cross section. This orange line is from this quasi-particle, from the first experiment, the qubit experiment. So you can see this is the strongest one. This magenta one is from the super CDMS experiment, the last one. The second experiment, the sensitivity, because the sensitivity from that experiment is not strong enough, so it's not, we did not show it here. It's outside of the range of this plot. And these gray lines, these are the all other existing experiments from, these are laboratory experiments, and these are some astrophysical observations. So you can see that even though these lines are not going into the new parts of the parameter space, but still it's still quite competitive with these other parts. And we also have to remember that these experiments, these are not dedicated experiments, in the sense that none of these experiments were actually trying to measure some excess power deposition from dark matter. So, and even from these experiments, we are getting this limit. So if someone can actually build one of such experiments for dark matter and continue for some time, hopefully we can expect to see even stronger power from this. So these are for halo dark matter, and this blue line is for thermalized dark matter, the captured dark matter, which I told you before. In this case, we are not limited by the sensitivity of the device or the detector. We are limited by the evaporation. So this line here, which is the limiting line here, is the evaporation line. What I mean by evaporation is that because it's a captured population of dark matter, if dark matter is very light, then the thermal motion in the environment itself will be large enough to kick out these dark matter particles from the Earth. So the final velocity of this dark matter particle will be larger than the escape velocity, and it will just escape to the infinity. So you do not expect to see this large population of dark matter for very low mass. So that's what limiting us. Otherwise, we would have gotten a large, much more stronger sensitivity for this population as well. So this is the main result. And in a later paper, we also extended that to subfraction dark matter. So for several models, you can have like multiple components of dark matter, and maybe you can, in that case, you can define a new parameter f chi, which is a fraction of dark matter. And we plot this same bound for this captured dark matter and overlap that with all other existing experiments. So you can see, for if you go below like 10 to the minus 3 to 10 to the minus 6, much of these other experiments, they start to vanish because they are looking at the halo dark matter, and their sensitivity is directly proportional to the number density. And if you have small fraction, dark matter fraction, their sensitivity is also gone. But that's not the case for this transmon qubit experiment. Our sensitivity is mostly intact. because we are looking at the captured dark matter. And so at some point, it's actually becomes the most sensitive one in this part of the parameter space. And this again, this to look at the some of what is some future prospect for in this direction. This gray region here is existing one, which I showed a couple of slides back. This I should remind you, this is for the halo dark matter again, and these colored contours are for other different other experiments. And I am showing these two other lines, these dashed lines, and we optimistically assumed a lower quasi-particle number density, 10 to the -3. I say also optimistically, but I think it is achievable within maybe, let's say, next 3 to 4 years itself. And if we can do that, we can expect to probe a smaller cross section all the way to maybe 10 to the -31 or -32 centimeters square with this qubit devices. So, and which kind of goes to the new parts of the parameter space. So this, in our opinion, this is actually quite promising, and it's worth investigating more and perhaps building a new experiment, because this type of experiment, these are very small scale, literal tabletop experiment, doesn't require a lot of funding, and doesn't require a lot of space, and very easy to do, and but still you get a large very interesting result out of that experiment. So, which is really cool in my opinion. Now, all of this is about putting constraints on the dark matter-nucleon scattering, right? If you actually want to claim a detection of dark matter, you have to do a little bit more work, because this is where the disadvantage of this method lies compared to the recoil experiments. Because it's not a recoil, you have to isolate the power, all other background powers. There are always backgrounds. You have to isolate the power coming from the dark matter from the all other background sources, and that's more challenging than doing a recoil experiment. So that's a main I would say downside for power deposition technique. And on top of that, there are all these other conventional sources of backgrounds, thermal neutron scattering from the environment, the radioactivities, cosmic rays, but these are, we know how to get rid of them, because these appear in other experiments also. You have to do proper shielding, and to build your experiments in an underground lab. And finally, because these experiments are in the low energy, and which is not very well explored even today, and there could be some unknown systematics and some excess powers which we do not yet know. And to claim detection, we also have to get rid of them, or we have to we will need to know what's causing them, and have to have our sensitivity below that. So these are some of the challenges challenges that we can face in this type of experiment. So that's going to be all. And just to summarize, we in these papers we proposed a new type of experiments, and because this in the light dark matter regime, there are many different ideas, and we do not yet know what's going to work for the best, and so we have to keep our mind open. And in this new technique, the advantage of this new technique is that we already have very good sensitivities and very capable technology for this qubits, especially in the transmon qubit community, and we can directly take the technology from them and build some interesting experiments and get some results. And as I said, the sensitivity also very good for subfractional dark matter, when the dark matter in question does not form the 100% of the density, cosmic density. And realistically, in next few years, we we can expect to improve this the limits from this type of experiments, maybe a few orders of magnitude, realistically speaking. And if we actually plan to do any experiment along this line, we can expect to do even that. So that's really positive. And okay, I'll just stop here, and thank you very much for your attention.
Thank you for a nice talk. Any other questions or comments?
Okay, so you use the this superconducting or the transmon qubit as a detector for the conventional dark matter scattering, right?
Yes.
But in the case, okay, so your proposal is like consist of the two part. One is like this scattering using those aluminum or silicon. The other is this detector like superconducting or the transmon qubit. Am I right?
So actually they're together. So
yeah, they are together, but yeah, nearby. So they are just like a cover, like a coating, like a, yeah, in your previous slide, right? You have this scattering and then yeah, over there, yes.
Yeah. So for example, in this case, the transmon qubit itself is made of it itself is made of superconducting aluminum, and that we are using this aluminum as the main absorbing material or the main detector material for us.
Okay, so for example, yeah, for the scattering case, your benchmark temperature like 100 millikelvin, but
yes,
for the transmon qubit, it should be the lower than the 100 millikelvin, right? Otherwise, the qubit will just broken.
So you mean here?
Yeah, for example, yes. So yeah, you are detecting this is like a 3 benchmark, like 100 millikelvin or 50 millikelvin, but the transmon qubit require like order of 1 millikelvin.
Right. So in the,
how can you use
so
the
in this, right? So yeah, maybe I can yeah. Let me see if I have the backup slide for that. Yes, no. So here what I did is just so this number density, this quasi-particle number density, it's a sum of two quantities. One is the quasi-particles that are being excited by dark matter, and the other is thermally excited. At any temperature, there is a thermal population of quasi-particles, and as you lower the temperature, that population also goes down. So that component, the thermal component, is kind of gone here already by 50 millikelvin. So even if you go below 50, let's say 1 millikelvin, this number is not going to go down anymore. So in this case, below 50 millikelvin, roughly speaking, we are only limited by the dark matter scattering strength. So the temperature is not the limiting factor anymore. Does that make sense?
No, what I mean that the temperature may damage your transmon qubit. So here I already confused the okay, so it's already confused. So okay, for example, you have the two cases. One is the like this silicon whatever, like for the target material, and the other is okay. One is the target, the other is the detector, right?
Yes.
And then if you go to your previous slide, yeah, over there, yes. So there's blue is a target, and this the upper is a kind of detector.
Right.
No. Yeah, detector. So in the case of when you use the So in the case of when you use the transmon qubit, for example, I don't understand because if I remember the transmon qubit is very fragile, so that you need to lower down your temperature like out of millikelvin. But your studies are like 50 millikelvin or 100 millikelvin, but that may damage your transmon qubit. That is my confusion.
Right. So you're right. I mean, in most of the advanced transmon qubit experiments, that the temperature is of the order of few millikelvin, and so as I said, but if you do the calculations for the quasi-particles coming from the dark matter and from the thermal, the thermal density is already gone below 50 millikelvin. So the curve will not change if you take, let's say, 1 millikelvin here. So that it will be the same here. But
Okay.
as far as this particular supersede image experiment is concerned, they are not using qubits. So their device is
Yeah. In the
different.
case I understand, but yeah, for the case of transmon qubit, I just got confused because your recent paper is also about this in the JEP style.
Right.
Like transmon qubit, also you use the same benchmark temperature, so that is my confusion.
Yeah. Okay, I see. Yeah, but no. Yeah, you were right that typically the qubit experiments use much lower temperature. We just stopped at here because, yeah, I mean, after below this, the thermal population already gone here. It's gonna be the same anyway. So that was the whole reason. Yeah.
Any other questions or comments? If not, let's thank to the speaker again. Thank you so much.
Thank you very much.
Thank you very much. Yeah. By the way, before I have one announcement. We have another seminar 30 minutes later. Exactly 3:30. Please remember it. Yeah, and then thank you for the talk again. Anirban.
Here, no problem.
Yeah.
I'll send you the slides. Yeah.
Yeah. By the way, do you remember me? My face?
Yeah, I do.
Yeah. When you
I
give a
do.
talk, when you gave a talk in class, I asked you, in the early stage of your talk. Yeah, that's the
Oh,
reason
I see.
why. Yeah, that's the reason why I was laughing when I see you just before the seminar. Yeah, since I remember your
Okay.
face. Oh, okay.
Yeah,
Really,
sure.
really thank you for giving the seminar. Yeah. And in a
Sure.
few
Yeah,
days,
no problem.
in a few days, our staff will contact you to give an honorarium, and then just after seminar, when you are convenient, then please give me your slide.
Yeah, I can send it
Yeah.
to you right away. Yeah.
I see. Thank you. Yeah. Have a good day. Yeah.
Thank you very much. Yeah.
Thank you
Too.
very much.
Thanks.
Yeah.
Yeah. Bye.